second type of rotation in section 5.2 involves rotating still, so it's still going to involve circles, but this time, sometimes what we're rotating around isn't really touched, and our axis is through the middle. So when that happens, each slice, you can see here in this picture, each slice is more of a washer than a disc. Disc was solid, no hole in the middle. Washer has a hole in the middle. Or a super smashed donut has a hole in the middle. So it's going to make our formula slightly different. Because when we have a washer like we have here, we have what it's rotating around, and we have two different radiuses. We have what I'm going to call little r, which is the radius of the inner function, the closer function to what we are rotating around, and then what I call big R, which is the radius of the function further away from our axis that we are rotating around. So, how would you find the area of a washer? Well, you take the area of the outside circle, which would be pi r squared, and you subtract the area of the inside circle. And that represents the area, and then we would multiply by dx or dy, depending if the thickness of our washer is an x value or a y value. So, let's try some. It says, find the volume of the region R enclosed by the curves y equals x, and y equals x squared. Well, if you know much about y equals x and y equals x squared, you know that they intersect at 0, 0, and they intersect at 1, 1. Sometimes you will have to calculate those intersections. Sometimes you know enough about the functions to know where they intersect. So, we've got y equals x, we've got x squared, and we're taking this enclosed little kind of crescent-shaped shape, and we are rotating it about the x-axis. So, it ends up looking something like this. And what happens is that we have a little radius in the middle that is actually a hole in each of our slices. And I'm going to switch colors. A bigger circle on the outside that is our big R will help us get. So, let's talk about that. Our generic formula is pi big R squared minus pi little r squared, and whatever the thickness of each slice is, in this case, our slice thickness is going to be an x value. So this is going to be in terms of x, dx. And we know that our limits of integration are going to be from 0 to 1, because our x value here is a 0, our x value here is a 1. And we get pi big R. Let's talk about big R for a second. Big R is going to be the distance from the straight line, this one, to the x-axis, which, no matter where you do it, is x. Little r is going to be the distance from our curve here, our x squared curve, to the x-axis, which, no matter where you do it, is going to be x squared. And again, the dx, because the thickness of our washers is dx. Now, all we have to do is calculate this. I'll simplify a little bit first. We've got the integral from 0 to 1. Pull our pi out front. And again, I'm pulling the pi out front, so both of them are gone. X squared minus x to the fourth dx. So I've got my pi. We need to anti-derive. 1/3 x cubed minus 1/5 x to the fifth from 0 to 1. And we got to plug in our 1, which gives us, I'm going to leave my pi out front for a second. Plug in the 1, we get 1/3 minus 1/5. Plug in our 0, we get 0. And 1/3 minus 1/5 is 2/15 pi. Or 2 pi over 15, because this is 5/15, this is 3/15. So we get 2/15 pi. You could also write that as 2 pi over 15. I like to put my pi at the top slot. I don't know why, just to have it. Let's try another one. Very similar. This time we're going to rotate it around the line y equals 2. So some funny things sometimes happen. We're talking about the same region. So it's still, I'm just going to take the region from an earlier problem, still that shape, from 0, 0 down here to 1, 1 up here. And it's going to be rotated about the line y equals 2, which means this is 1. It's actually going to end up here between 3 and 4 when it's rotated. And we end up with the inner radius and the outer radius. So these still look like washers, almost a bracelet because the hole in the middle is really big, but technically still a washer. And our formula for a washer, pi big R squared minus pi little r squared. And the thickness of each washer is going to be an x value. So our limits of integration are from still 0 to 1, because they start at the x-axis and they go to this point, 0 to 1. Big R, we have to think about how long our big radius is. So always draw from this line we're rotating around to the original. So our big R is going to be this long. Or, just like our rectangle, top minus bottom, the top is a 2. The bottom, top is a 2. The bottom is this x squared. So 2 minus x squared. Minus pi, and our little r, I'm going to grab another color, let's do some purple. Our little r is this distance, or this distance, from the horizontal line of 2 to that y equals x line. So if we take the top minus the bottom, it's 2 minus x squared dx. Now, our pi can come out front, and we get 2 minus x squared squared minus 2 minus x squared dx, and they're stacked from 0 to 1. If we simplify this a little bit, we get pi 0 to 1, 2 minus 4, oh, sorry, not 2. I'm squaring this. We get 4 minus 4x squared plus x to the 4th minus 4 minus 4x plus x squared. I'm going to go ahead and distribute my negative. And if I combine like terms, oh, not 0 to pi, 0 to 1, my pi out front, my 4s are gone. I've got x to the 4th minus minus 3x squared plus 4x. I think. tomorrow with that as a question. All right, let's try one more. This time it's going to rotate about the y-axis, so it's going to be a slightly different. It says find the volume of the region enclosed by y equals 2x and x equals 2y as it is rotated about the y-axis. Well, in order to graph these, we need to solve them for y. And we end up with this line, y equals x over 2, which starts at 0 and goes up 1 over 2. And this line, radical x, which also starts at 0, curves up and at scratch that. Whoa, okay. This goes up 1/2 to 2, up 1 over 2, up 1 over 2 again, gets us at the point 4, 2. And then radical x goes through 0, 1, and also goes through 4, 2, because the square root of 4 is 2. So, when we take this shape and we rotate it about the y-axis, we end up running into discs, washers actually, because they have holes in the middle that are stacked from bottom to top. So again, this time I'm going to put my pi out front right from the start. These washers are stacked from 0, because this is where they start, up to here, which is a 2. We need big R squared. Let's talk about big R for a second. Big R is the distance from what we rotated around to this straight line. And we need to be in terms of y. So we're talking about this function. So instead of putting x over 2, we're going to put 2y. We actually take 2y minus the 0. Subtract from right to left, squared for big R. Minus little r squared. Well, little r is going to be the distance from this curved line to the x-axis. The curved line was radical x, but in terms of y, it's really y squared. So y squared squared, and the thickness of each of these washers is a y. So we have pi. If I simplify this a little bit, we get 4y squared minus y to the 4th. By this point, you guys are very good at solving integrals. Please solve that and make sure you come out with the answer of 64 pi over 15. Please take good notes on this today. Watch it again if you need to without writing anything, just so it soaks into your head, and come tomorrow with questions.